Okay, so in the last video we took a look at coupled harmonic oscillators using Newtonian formulation. Now we're going to revisit it using a Lagrangian formulation. And specifically we'll pick up where we left off, so we won't do the general problem. We'll just look at the case of the identical masses, identical springs attached to the walls, allowing for a possibility of a different spring on the inside. Well, that's generalized coordinate x1, that's generalized coordinate x2 measured off the respective equilibria positions. Alright, so with that we can go ahead and write our kinetic and potential energies. The kinetic energy will be 1/2 m x1 dot squared plus 1/2 m x2 dot squared. The potential energy will be 1/2 k x1 squared plus 1/2 k x2 squared plus 1/2 k prime, and this is what in the jargon we call a coupling term. x2 minus x1 squared is a coupling term because it depends on both coordinates. This term depends just on the x1, this depends on the x2. This is usually what gets called a coupling term here. Alright, so let's go ahead and expand that out. 1/2 k x1 squared plus 1/2 k x2 squared, because we're looking to get this into a matrix formulation again, plus 1/2 k prime. Let's see, we're going to get a k prime x2 squared plus 1/2 k prime x1 squared, and then we got the cross terms. Will be minus 2 times 1/2 is just minus k prime x1 x2. And so most specifically, this is the coupling term here. Everything else we could deal with. Alright. So we can rewrite the potential energy as 1/2, grouping matching terms, k plus k prime x1 squared plus 1/2 k plus k prime x2 squared minus k prime x1 x2. Alright, so now we can go ahead and write this in matrix form. And now I'm going to switch up and use Blackboard Bold writing for my matrices, just because I'm going to have to start taking transposes, and I thought it might be more confusing if I switched away from using twiddles to using backward arrowheads on vectors. So I'm going to switch to using a Blackboard Bold notation for these matrices. So we can write the kinetic energy as 1/2. So we're going to have a x dot twiddle m x dot. So that would be written as 1/2 x1 dot x2 dot m00 m x1 dot x2 dot, like so. And similarly for the potential energy, we can write that one as 1/2 x twiddle k x. So that'd be 1/2 x1 x2 k plus k prime minus k prime minus k prime k plus k prime x1 x2, like that. So then my Lagrangian, which is t minus v, will be 1/2 x dot twiddle m x dot minus 1/2 x twiddle k x. Alright. And just for completeness sake, we'll just note that that still works out to be 1/2 m x1 dot squared plus 1/2 m x2 dot squared plus 1/2 k plus k prime x1 squared plus 1/2 k plus k prime x2 squared minus k prime x1 x2. So it all checks out. Alright, so let's go ahead and start writing Lagrange's equations of motion. So that'll be partial L partial x1 minus d dt of partial L partial x1 dot equals 0, and partial L partial x2 minus d dt of partial L partial x2 dot equals 0. So that's my system, right? So let's go ahead and evaluate that. So what do we have with x's in it? Okay, we've got this guy here. Bring down the 2, cancels the half. So we get k plus k prime x1. And then this guy here's got an x1, so I'll have minus k prime x2 after I do that partial derivative. And that's it for the x1. So now we go looking for the x1 dots. It's only here, so bring down the 2 to cancel the half. So it'll be minus m x1 dot, but then we time differentiate, so we get double dot equals 0. And then for x2, that one's going to be, let's see, I got an x2 here, bring down the half, cancel, so it'll give me k plus k prime x2. Then here, differentiate with respect to that x2, I'll be left with an x1 minus k prime x1. And then this will give me minus mx2 double dot equals 0. So you can see this is a coupled system. All right. So we can go ahead, move these over to the other side. We'll have mx1 double dot equals k plus k prime x1 minus k prime x2, and mx2 double dot equals minus k prime x1 plus k prime x2. So just like before, we wind up getting, if we write it back in matrix notation, m times x double dot equals minus k times x. All right, so glad to see that that checks out. All right, so with that thought then, we should ask ourselves, what do we make of, so if we solve it, we'll get the same thing that we did before. No need retreading that. So we'll get down to the same Q's we had before. So what do we make of the Q's? All right, so first thing we can say about them is we got them from an eigenvalue problem. So that means that if I dot Q1 with Q2, so writing them as matrices, Q1 twiddle, Q2, they have to be 0, right? So let's just double check that that's true just for the grins. So when we do that, this is going to be A1 cosine omega 1t minus delta 1. I'll put the row vector for this at the end. And then this gave me an A2 cosine omega 2t minus delta 2. Okay, the row vector we'll get from this guy is 1, 1. The column vector we'll get from this guy is minus 1, 1. Okay, well let's multiply these together. Minus 1 plus 1, 0. So yeah, they are indeed orthogonal. What that means though is that we can use these vectors as a basis. So the Q's are a basis for our solutions. So from a kind of more physicsy approach, we can look at what we call configuration space, where we put x1 like this and x2 like that. And if I were to draw in the q's, that would correspond to q1, and that would correspond to q2. And we would get that our basis is rotated 45 degrees off of our configuration space. So what does that mean there? This means that sometimes, rather than trying to gut it through, I mean, you can always solve the eigenvalue problem, well, until they get too big. You can always solve the eigenvalue, eigenvector problem, but that can be kind of a rough way to go. So the trick is that sometimes you can just look at the problem. So if we go ahead and look at this, with a little bit of experience, you would say to yourself, well, what would be my two normal modes of oscillation? And I think you would at least get the symmetric mode out of it right away, where the spring is the least involved. And then you could guess, well, what would be the case where it's the most involved? And then you would come up with the breathing mode. So if you have that, then maybe you could just go ahead and write your configuration basis right away. So that's the idea. So then we can so if we can write down the q's right away, our goal is that we should be able to write our x's as some transformation matrix times our configuration basis. Or if we want to go back the other way, you could write it as the inverse of our transformation matrix times our physical space. All right. So just to make things go simpler going forward, let's let delta 1 equal delta 2 equals 0, and we'll let a1 equal a2 equal 1 over root 2, just so we have some things nicely normalized. So if we do something like that, we could look and just start writing that our q1, I guess I should, no, I'll leave it as a vector arrow. No, well, there we go. We'll write our q1 as 1 over root 2, 1, 1, cos omega 1 t. So we're getting that just from directly observing, based on our experience, that we should have a symmetric mode of oscillation. And we could also directly write that our q2 is 1 over root 2 minus 1, 1, cos omega 2t, on the same idea. So then my claim here is I could write my x's. So we'll do this on a guess and check approach. I can write my x's as 1 over root 2 q1 plus q2, right? So if I do that, this 1 over root 2, both these guys have 1 over root 2, so when I multiply through, I'm going to get a half, okay? And then I'll just be left with what? Cos omega 1t minus cos omega 2t, and cos omega 1t plus cos omega 2t. So yeah, those mesh up with exactly what we would expect the antisymmetric and the symmetric modes to look like. All right. So we can then conclude that our x1 is 1, our x1, sorry, is 1 over root 2 q1 plus q2, and our x2 is 1 over root 2 q1 minus q2. All right. So we'll go ahead and let, oh, oops, sorry. These shouldn't be vectors. Oh. There. Our x1, x2, the actual generalized coordinates. There, pick him out like that. So we'll let q1 equal 1 over root 2 cos omega 1t and q2 equal 1 over root 2 cos omega 2t. All right, so now we're on the way to get our transformation matrix. We can write our transformation matrix x as being 1 over root 2, and then to get the first of these solutions, I'm going to have 1 minus 1. And to get this solution, I'm going to have 1, 1 times our Q matrix, right? So that means we can go ahead and identify the 1 over root 2 times that as being my A. And so then I can also get, if I need it, that my A inverse, thank God it's an orthogonal, an orthonormal matrix, I can write as 1, 1 minus 1, 1. So I will observe that that's also equal to A transpose. All right, so now that we've got these normal coordinates set up, we can look back at solving the Lagrangian in these normal coordinates. So I can write my t again, just a reminder, that was 1/2 x dot twiddle m x dot. Well, if I think about it here, I can write my x as being a q, right? And so then that means x twiddle would be equal to a q with a big twiddle, which remember is the same thing as q twiddle, whoa, a twiddle. All right, so putting that in, we can write this as 1/2. So from here with the transpose, that will become a q dot twiddle, a twiddle. I still get my m. And then from here, I'm going to have an a q. All right, that all looks good. So I look at this a twiddle m a. That's going to be a diagonal matrix, so we're just going to go ahead and call it m diag. All right. And let's just verify that that's true. So that'll equal, so I'm going to have a twiddle m a. From both the a twiddle and the a, I'm going to pick up a 1 over root 2, so I'll have 1 over root 2 squared. And then let's see, I'm going to be timesing 1, 1 minus 1, 1, m 0, 0, m 1 minus 1, 1, 1, right? So we get a half. All right, so let's go ahead and we'll do 1, 1 minus 1, 1. We'll do this one first. We'll get an m in the, right, m, right, for that. And then minus m goes here. And then here we get m here. And then we get m there. All right. And then we'll get 1/2 doing this one. So it's going to give me, 2m there, 0 there, 0 there, 2m there. So half times 2 just leaves us m 0, 0, m. So yeah, it turns out that in this case, the diagonalized, since it was already diagonalized, my m diagonal is indeed equal to m. All right. Now it'll turn out that for the k's, we'll get a lot cleaner matrix to play with, and that's why working in this basis is going to be useful. So we'll write our potential energy as 1/2 x twiddle k x, and we'll do the same transformation here. So we're going to get 1/2 q twiddle a twiddle k a q. And we'll look at this and call this, whoa, k diag, like so. All right. So since I'm claiming that's going to be diagonalized, I think it's worth us checking that claim, huh? So that will be, so k diag will be, so again, same deal, we get 1 over root 2 squared from the normalization, and then we do the similarity transform here, 1, 1, minus 1, 1, k plus k prime minus k prime minus k prime, k plus k prime, 1 minus 1, 1, 1, so alright, so this becomes 1/2, 1, 1 minus 1, 1. Alright, let's do the matrix multiply. So do k plus k prime minus k prime is just going to give me k there. Then for this one, I'll have minus k prime, and then that's minus k prime there. So I'm going to have minus k minus 2k prime. And then let's see here, this will be minus k prime plus k prime, so this gives me k again. And then here, minus and minus is a plus k prime, so this is going to be, and then, yeah, so this will be k plus 2k prime. And then let's go ahead and do the next multiply, so I have 1/2 times, doing that gives me 2k. Doing this gives me 0. Doing this gives me 0. Doing this gives me 2k plus 4k prime. Okay, multiply through by the 1/2, and I get k 0, 0, k plus 2k prime. So working in this configuration space is a lot more convenient, because now my spring constant matrix is diagonalized. So that gets rid of the coupling between the differential in our differential equations. So let's go ahead and in this basis work to actually solve the Lagrange's equations of motion again. So alright, L equals T minus V. So in this basis here, we'll have that this is 1/2. So we've got a Q1 dot, Q2 dot. My mass matrix is M0, 0, M. Q1 dot, Q2 dot, minus. I'm going to move everybody over. There we go. Minus 1/2. I'll have a Q1, Q2 here. And then I'm going to have K0, 0, K plus 2K prime, Q1, Q2, like that. Alright. So let's actually do the matrix multiplies. So this becomes 1/2. So when you do this, you're just going to get what? A column vector of M, Q1, M, Q2 with dots. And then, yeah, this is going to become 1/2 M, Q1 dot squared plus 1/2 M, Q2 dot squared. Then let's see here, it's going to be the same drill, minus 1/2 K Q1 squared minus 1/2 k plus 2k prime q2 squared. Oh, this will be so much nicer now that we don't have that coupling term between q1 and q2 like we did between the x1 and x2. So let's go ahead and write down and solve Lagrange's equations of motion for this system. So partial L partial q1 minus d dt of partial L partial q1 dot equals 0. Alright, so differentiating that's just going to give me minus k q1. This is going to give me minus m q1 double dot equals 0. So getting the standard form q1 double dot plus k over m q1 equals 0. My God, that is a simple harmonic oscillator, and that is omega 1 squared. Similarly, partial L partial q2 minus d dt of partial L partial q2 dot equals 0. So this will become minus k q2 minus m, oops, I lied, minus k plus 2k prime q2 minus m q2 double dot equals 0. So I get q2 double dot plus k plus 2k prime over m q2 equals 0. And again, we're going to say, oh, that's a simple harmonic oscillator. I know what to do with that, and that is omega 2 squared. So we get exactly the same results as before, just with a lot less effort. So it pays to spend just a little bit of time, see if you can find a symmetry in the system. If you can find a symmetry in the system, then maybe that will allow you to construct your basis. Then you can go from there. Even if you have to start by putting it all into Cartesian, maybe you can play with it a bit then to see if there's a basis you can transform it to, which will be diagonalized, and you know that you can generally do that, at least with anything well behaved. Just go ahead and bring up your tools of linear algebra to do it. So it helps to speed things up. Now, here's an important note. You run into this a lot in quantum mechanics. If you've taken modern physics already, you will have already seen this. So let's say that our coupling K prime, if that coupling K prime didn't exist, so then you just have two masses on springs, I guess, that you let roll. You would have omega 1 squared equals omega 2 squared. So we call that a degeneracy. The system admits for two possible solutions, but they both happen to have exactly the same frequency. This happens in quantum mechanics a fair amount, that sometimes the system is degenerate, we call it. But if you can put some kind of a weak coupling into the system, then instead of your energy levels, to use an energy level diagram from quantum mechanics, instead of your energy levels being shared, you now change them slightly, like that. And we say that we have lifted the degeneracy. A practical example from the field of quantum mechanics, for instance, would be if you put the system into a magnetic field that would induce a coupling, a weak coupling into the system, or possibly not so weak, but in any event it would move the energy levels around just that little bit, and you can lift the degeneracy. So for instance, the Zeeman effect would be a good example of that. All right. So while we're at it here, let's also note that our Q1 is equal to 1 over root 2 times 1, 1 cosine omega 1t, and our Q2 is equal to 1 over root 2 times minus 1, 1 cosine omega 2t. Let's not worry about the cosines so much. Let's look right here. These guys here are the normalized eigenvectors of K. So if you couldn't immediately intuit what the symmetries were, we could still get it. You can write your K matrix, and then you can just go ahead and find the eigenvectors. It's not, like I say, that if the system gets very large, that can go bad quickly. So you're still better off if you can buy yourself the eigenvectors somehow, or you can intuit it from the symmetry of the situation. That will help a lot. All right, so anyway, so following from that, we can go ahead and let our A1 equal 1 over root 2, 1, 1, and our A2 equal 1 over root 2 minus 1, 1. And so then we can get our transformation matrix A. So again, if you can intuit the symmetry, you can get the transformation matrix right away by writing it as a row matrix of A1, 1 and A1 and A2. So we go ahead and put in our A1 in the first column, 1, 1, put in our A2 in the second column, minus 1, 1. All right. So if you have, for some reason, or if you can guess the eigenvectors, that immediately allows you to diagonalize K and M. So here's an example of how you can do it. Sometimes you may not be able to immediately guess the eigenvectors like we did there, but sometimes you can just stare at the Lagrangian for a while, and maybe you can find a symmetry there. So let's look at a more general case. We'll write that L is equal to T minus V, so that's still 1/2 x dot twiddle x dot, right? Minus 1/2 x twiddle k x. All right. So let's write this in a more general case. So this will be 1/2 x1 dot x2 dot. We'll write this as m11, m12. Now normally I should write this as m21, but I'm going to write as m12 because this has to be a real symmetric matrix, right? m22. And then similarly minus 1/2 x1, x2. We'll write this as k11, k12, and again, instead of writing k21, we'll write that as k12, because again, it has to be a real symmetric matrix, k22, x1, x2. Oops. Don't do that to me. All right, fine. x2. There, much better. All right. So if we write it out, we can get that L equals 1/2 m11 x1 dot squared plus m12 x1 dot x2 dot plus 1/2 m22 x2 dot squared minus 1/2 k11 x1 squared minus k12 x1 x2 minus 1/2 k22 x2 squared. All right. And if we look at this, we recognize, if you stare at this for a while, you might come to the realization that this Lagrangian would be invariant under a transformation where we let our x1 go map over to either a plus or minus, it doesn't matter, x2 over alpha, as long as we replace our x2 with either the same plus or the same minus, so those are tied together, alpha x1, right? Let's just go ahead and look at that. So if this becomes so let's just, like I said, this x1, x2 here, right? So this becomes x2 over alpha, that becomes alpha x1. We still have a product x1, x2, right? So let's go ahead and follow through what that means. So my transformed Lagrangian would become, so I'll just go ahead and make in all the substitutions here. So become 1/2 m11 x2 dot squared over alpha plus m12, so the x1 dot x2 dot plus 1/2 m22 alpha squared x1 dot. So I'm hoping we can do this for some value of alpha, and the answer is yes, we can. We just need to find them. Minus 1/2 k11 x2 squared over alpha minus k12 x1 x2 minus 1/2 k22 alpha squared x1. Okay, so we've made those substitutions, and we need. So maybe this transformation works, maybe it doesn't. But since it's going to work, what we're going to need my L prime to equal L. So let's go ahead and equate terms here between the L and the L prime. So equating the L and the L prime, let's look at this term here, in the m11 x1 dot squared, right? That matches to here m22 alpha squared x1 dot. So that's one of the first things that we get. It's m11 equals alpha squared m22. And by the same token, we get k11 equals alpha squared k22. And you can check the other way around, like let's go look here. This m22 x2 dot squared, if I match that over here, yeah, we're checking out. Okay, good. So this means that I can write my mass matrix as, I can replace the m11 with an alpha squared m22, m12, m12, m22, because we can see the 1, 2 terms here are still the same, right? And there, Okay, so that all works. And similarly, I would have to write my k as some alpha squared k22, k12, k12, k22, like so. All right. So we already know, if we go ahead and write Lagrange's equations of motion, we've found that we can write x double dot twiddle m x double dot minus x twiddle k x equals 0. That's what we get from the Lagrange's equations of motion. So that gives rise to the secular equation k minus omega squared m, just like before, times our eigenvector a equals 0. So again, we demand that the determinant k minus omega squared m equals 0, right? So let's see what we get from that. So that's going to be the determinant of, we'll have an alpha squared k22 minus omega squared m22, k12 minus omega squared m12, k12 minus omega squared m12, k22 minus omega squared m22. And we need that to be 0. So I'll just say, in the interest of time, you can go ahead and solve for the determinant of that, and you will get the eigenvalue omega squared equals alpha k22 plus or minus k12 over alpha m22 plus or minus m12. And the eigenvectors are 1 over alpha and minus 1 over alpha. So from that we can conclude that our transformation matrix has to be something like 1 over alpha minus 1 over alpha. So if we go back to what we had before, so as an example, we had a k that was k plus k prime minus k prime, sorry, those are k primes there, k plus k prime, right? So we need k11 to equal alpha squared k12, right? So k11 is k plus k prime. And that's equal k12 is minus k prime, so minus alpha squared k12, oops, sorry, k prime, right? And so what's going to work here to make that happen is alpha equals 1 will do the job. All right, so with that we get our transformation matrix that we found the hard way before. So just by finding that similarity, we could transformation invariance, that symmetry, that allowed us to deduce our basis. And then we could go ahead and solve the problem. All right, let's just finish this particular video off with an example, just to kind of show how we can work that. Whoops. So, for instance, let's have a ceiling, and we're going to attach 2 pendula. Both have a bob of mass m. So the obvious generalized coordinates are theta 1 and theta 2. And then we're going to put a weak spring, K, between the two. And while we're at it, we'll also pinky swear that the oscillations will be small. All right, so with that, we can go ahead and write that T is equal to 1/2 ml squared theta 1 dot squared plus 1/2 ml squared theta 2 dot squared. Now for V, we can write that as mgl, and I could put the origin up here, but because I've done this problem before, I know it's going to make more sense to put the origin down at the bottom of the swing. So 1 minus cosine theta 1 plus mgl 1 minus cos theta 2. I need to move that a bit. Plus, we have a coupling term now, plus 1/2 k, and this is why we need the small oscillations here, because we don't want this to pitch up too much in angle. So if we keep it small, we can say this distance is equal to L theta 1 here, and this distance here is L theta 2. So we can say that the total stretch is L times theta 2 minus theta 1. Square that, we get L squared times theta 2 minus theta 1 squared. All right, so we've already pinky sworn that this is a small oscillation in order to make this happen, so that we can say that this is still approximately horizontal. So while we're at it, we may as well go ahead and expand our cosines, right? So we know the cosines can be 1 minus 1/2 times theta 1 squared plus minus dot dot dot, and we're just going to keep the first non-unitary term, because when I put this in, this one's going to cancel. So we can write that our V is approximately 1/2 mgl theta 1 squared plus 1/2 mgl theta 2 squared plus 1/2 kl squared. Now here, let's go ahead and expand this out. Theta 1 squared plus 1/2 kl squared theta 2 squared plus our coupling term, right? Which will be minus kl squared theta 1 theta 2. All right, so getting this into some kind of matrix form, so we can think about it a little bit. 1/2 theta 1 theta 2. So our coupling matrix is going to look like mgl plus kl squared here, minus kl squared there, minus kl squared there, and mgl plus kl squared there, theta 1 theta 2. While we're at it, and so then we can identify this as my K matrix. All right, similarly, I could rewrite the potential energy T as 1/2 theta 1 dot theta 2 dot ml squared 0 0 ml squared theta 1 dot theta 2 dot, which is why these have to be generalized masses, because now we're dealing with moments of inertia there, but they'll play the role of a mass on TV. All right, so when we look at this, this turns out to be the same, this is chosen to be the same kind of layout as what we had before. So again, you could observe that you could have your theta 1 go to 1 over alpha theta 2, and your theta 2 go to alpha theta 1, just like before. And so you go ahead and do everything we just did before, and you'll get k11 equals alpha squared k12, and you will conclude that alpha equals 1 will do the job. So we can write our transformation matrix will be, we're going to throw in a 1 over root 2 just for normalization. 1, 1, minus 1, 1, right? So then our Q's will be 1 minus 1, 1, 1, theta 1, theta 2. So this becomes 1 over root 2, theta 1 minus theta 2, theta 1 plus theta 2. And you look at that and say, okay, this is my antisymmetric mode. And this is my symmetric mode. All right. In the final series of videos here, we'll be continuing our exploration of the dynamics of oscillating systems. And we're going to extend this into a general theory of vibrating systems. So we'll be extending it to multiple masses on our string, and then eventually take it to a continuous string to come up with the wave equation.